Transition metal atoms or ions with one or more unpaired electrons and their complexes exhibit color both in their solid and solution states. Let us see how a substance gets its color. When white light passes through a substance, it absorbs some of the wavelengths. The light transmitted by the substances is deprived of the wavelengths that have been absorbed. If absorption occurs in the visible region of the spectrum, then the transmitted light has a color complementary to the color of the light absorbed. Complementary color is the color generated from the wavelength left after the absorption. For example, for hexaaccure titanium 3+, the maximum absorption occurs at 498 nanometer, which corresponds to the blue-green portion of light. The transmitted light is devoid of the blue-green portion, and hence the complex appears purple. The relationship between the absorbed and transmitted wavelengths can be readily understood from the table here. The origin of the color of coordination compounds can be readily explained in terms of the crystal field theory. As you have studied in the previous module, when a ligand approaches the metal ion containing unpaired electrons, the 5 degenerate d orbitals separate into 2 distinct energy levels, namely T2G and Eg. When light of sufficient energy is incident on the metal ion, the electron in the low-energy T2G orbital absorbs energy and gets promoted to the higher Eg set of orbitals. White light minus the absorbed color becomes the color of the complex. Thus, the color of coordination compounds arises from the electron transition between the split d orbital energy levels. Let us take the example of hexaaccure titanium 3 to understand this. Hexaaccure titanium 3 is an octahedral complex, in which titanium is in +3 oxidation state and has a single electron in the d orbital. The single electron is present in the lower T2G level in the ground state of the complex. When light passes through a solution of this complex, the electron in the lower T2G level is promoted to a higher Eg level by absorbing light with energy equal to the energy difference between the T2G and Eg levels. In this case, it absorbs energy corresponding to the blue-green region. As white light minus blue-green light gives purple color, the complex appears purple. The color of gemstones like ruby and emerald is also due to the d to d transition of electrons within the d orbitals of the transition metal ion. Ruby is a pink to blood red colored gemstone. It is aluminium oxide in which a small fraction of Al3+ ions are replaced by chromium 3+ ions. The red color of a ruby is mainly due to the presence of chromium 3 ions. We may view these chromium 3 ions as octahedral chromium 3 complexes incorporated into the alumina lattice. This crystallographic arrangement affects each chromium 3+ ion. resulting in the D to D transition of electrons after the absorption of the yellow-green portion of light. As white light minus yellow-green gives red color, a ruby looks red. Emerald is a green variety of the mineral beryl. The green color of emerald is due to the presence of chromium 3+ ions. The chromium 3+ ions occupy the octahedral sites in beryl. Due to this arrangement, it absorbs the yellow-red portion of light and, in turn, transmits the complementary color green. Hence, an emerald appears green. It is important to note that in the absence of a ligand, crystal field splitting does not occur. As a result, the substance remains colorless. For example, when hexa-aqua titanium 3+ is dehydrated by heating it, it becomes colorless. Similarly, hydrated copper sulfate is blue, while anhydrous copper sulfate is colorless. The influence of the ligand on the color of a complex may be demonstrated by considering the hexa-aqua nickel-2 complex. When nickel-2 chloride is dissolved in water, it gives the green hexa-aqua nickel-2 complex. To this complex, if the didentate ligand ethane 1,2-diamine is added progressively in different molar ratios, different complexes with varying colors are formed. When the addition of ethane 1,2-diamine to the complex is in the molar ratio of 1:1, a pale blue colored complex of tetra-aqua ethane 1,2-diamine nickel-2 is formed. When the addition is in the ratio of 2:1, a blue or purple colored di-aqua bis ethane 1,2-diamine nickel-2 is formed. Addition in the ratio of 3:1 results in a violet colored tris ethane 1,2-diamine nickel-2 complex. Now let us see the drawbacks of the crystal field theory. Although it successfully explains the formation, structure, color, and magnetic properties of coordination compounds satisfactorily to a large extent, it suffers from some drawbacks. If the assumption that anionic ligands are point charges is correct, then anionic ligands should act as strong ligands, and hence should exert the greater splitting effect. However, anionic ligands are actually found at the low end of the spectrochemical series. The other drawback is that it does not take into account the covalent character of bonding between the ligand and the central atom.